beginning, Benny Bachner will talk about LP approximations and stability for groups. Benny, thank you.
Okay, thank you. So this talk will be somewhat connected to the previous talk where Alon talked about stability. So first we will talk about the general framework of metric approximations of groups, which encapsulates some major open problems in group theory and in operator algebras. And we will survey some results from recent years, and then we will talk about our contribution. So during our talk, we will always talk about gamma, a discrete countable group. And we look at the following. So we have G, which is some family of tuples of groups Gn and metrics Gn. Okay, so some family of groups which we should think of them about, say, finite groups or linear groups or some groups that we understand well that we want to approximate gamma by. And we will say that gamma is approximated by the family G if the following two conditions hold. So first of all, there is a sequence. Okay, if there exists a family of maps phi n from gamma to Gn in the groups that satisfy the following two properties. So the first is being asymptotically multiplicative, meaning we have for any G and H in our group, we have that the distance between phi n of gh, phi n of g, phi n of h approaches 0. Okay, this will be called asymptotic homomorphism. And the second property that we want every group element to be asymptotically separated from the identity. Okay, so for any non-trivial element G in the group, we have the lim inf of dn, the distance between phi n of G and the unit. We want this to be strictly greater than 0. And this also has a natural interpretation in terms of ultra products. Okay, equivalently, we have gamma embeds into what we call the metric ultra product of the family Gn and Dn with respect to some non-principal ultrafilter omega, which is simply the direct product of Gn's, and we mod out by the normal subgroup n omega, which is simply defined by all the sequences Gn whose distance from the identity approaches 0. Okay, and one can check that it is equivalent to give an embedding of gamma into this ultra product and to have an asymptotic and to have an approximation of our group gamma. Okay, and so this is the general framework, and if we look at particular cases, okay, so special cases, so if we take the groups Gn to be finite symmetric groups, and we take the normalized Hamming metric, okay, so this is the normalized number of points k on which, okay, bham of sigma and tau, the points on which they disagree. Sigma of k is different from tau of k. Okay, and these groups are called Sophic groups, and it is so it was studied by Gromov and termed by Benji Weiss, and it is a major open problem of whether there are any groups which are not Sophic. Another important class of groups relates to the talk of Michael, the Hilbert-Schmidt norm. So we have Gn, the unitary groups, U of n, and we take the normalized Hilbert-Schmidt norm. Okay, this is 1 over n, trace of A star A, one half. Okay, and these groups are called hyperlinear groups. And by the negative answer to Kahn's embedding problem, we know that there are Von-Neumann algebras that are not Kahn-embeddable, but it is still an open problem of whether there is a group algebra, a Von-Neumann group algebra, which is not Kahn-embeddable, which in such groups are called hyperlinear groups. And another case, okay, from now on we will always look at Gn defined by the unitary groups. Okay, and we consider the operator norm. So these groups are called MF. This goes back to work of Blackadar and Kirchberg, and this is also still an open problem of whether there are groups which are, they define it in general for C-star algebras, but it is still not known whether there are groups which are not approximated by the operator norm. It is yes, it is known that there are non-MF C-star algebras, but not ones that arise from groups.
What does MF stand for?
Yeah, matricial field, which doesn't say anything. Like, I was told that there is a reason why it's called that.
You don't normalize the operator norm.
No.
It's clear, like, when to normalize and how?
Like,
it's sensitive, right?
The operator norm is bounded.
Yeah, I know.
yeah, no, the operator norm we don't normalize.
It's one
It's one
And this brings us also to the and so we will talk about another family of groups. Okay, we will focus ourselves when Gn once again is the unitary groups, and the norm is given by the p-Schatten norm. The p-Schatten norm of a matrix A, is defined by the trace of the absolute value of a, which is square root of a star a to the pth power, and then we take 1 over p. So these are all, by the way, bi-invariant norms. So for matrix A, we can take the singular value decomposition, and the way I like to think about it is just it is simply the p norm of the vector of singular values of A. And two special cases, okay, so the 2 norm, okay, so remember I talked about the normalized Hilbert-Schmidt norm, so the 2 norm we will call the unnormalized Hilbert-Schmidt norm the Frobenius norm. For fixed n, any 2 norms are by Lifshitz equivalent, but when we look asymptotically, they behave entirely differently. And when we take, okay, we have p between 1 and infinity, where infinity corresponds to the operator norm. Okay, because for fixed n, if we take p to infinity, we simply get the operator norm. And so let's talk a little about stability. So gamma is G stable if for any asymptotic homomorphism phi n there exists a sequence of psi n of true homomorphisms such that they are asymptotically close, so such that for every g the distance between phi n of g and psi n of g goes to 0. Okay, so once again we demand that so a way to produce an asymptotic homomorphism is to take a homomorphism and take some small perturbation of that, and stability says that this is the only way in which asymptotic homomorphisms arise. And even for a fixed group gamma, the question of stability can depend heavily on the groups and the norms that we consider. For example, Alon mentioned that abelian groups are stable in the normalized Hilbert-Schmidt norm, but for example, in the operator norm, a classic example by Voiculescu shows that pairs of unitaries that almost commute in the operator norm are not necessarily close to commuting matrices, and this is, by the way, true for all p-Schatten norms.
Non-normalized p-Schatten, like the usual.
Yes, the usual p-Schatten norm. So the normalized Hilbert-Schmidt is stable for abelian groups, and the unnormalized is not. Okay, so we will talk a little bit about so we recall a higher property T from Uri's talk. And this is intimately connected to stability of specifically in the Frobenius norm. So recall the definition. Gamma has property Tn with square brackets if for any I between 1 and n minus 1, and we have cohomology Hj of gamma pi equals 0 for any unitary representation pi of gamma on some Hilbert space.
Why n minus one?
Sorry. N. Thank you. And it has property Tn with circular brackets. If the same holds, for pi with no non-trivial fixed vectors. Okay, so this simply says that non-trivial cohomology has to arise from the trivial representation. And so a classical classic theorem by Garland and later improved by Bollmann-Swiatowski says that if G is a simple QL algebraic group, of rank R, and gamma is a lattice in G of QL, okay, well, it is necessarily a co-compact lattice, as all lattices in these groups are co-compact, then gamma has TR minus 1. Okay, so these groups have, and I should mention that T1 is equivalent to property T, which is why this is termed higher property T. And yes.
So the Garland and the Bachner-Swiatowski thing, it assumes that they assume that L is big.
Right. Yes. For a large enough.
But it's correct for all L, and this is by Izar Oppenheim and Zohar Reisbaum.
Okay. So yeah. So L large.
Or vice versa, Oppenheim and
Okay. And in a much more recent result by Bader and Sowell, has a similar property, so the slightly weaker property for real Lie groups. So if G is a connected simple Lie group, of rank R, and gamma is a lattice.
Could be finite volume.
Yes, it doesn't have to be a uniform lattice. Then, well, there are some slight cases, but let's say in most cases, gamma has TR minus 1. Okay, so it in all cases, sorry. Then
So
This is round and that one's square?
Yes, this one is round because it can have non-trivial cohomology with respect to the trivial presentation, but all the other ones vanish. And the relation to stability is the following. So a theorem by Deshifre, Glebsky, Lubotzky, Tom in 19 is that groups with square bracket T2 are G2 stable. Okay, so Frobenius stable. They are stable with respect to the Frobenius norm. And so to give an idea of why this is true, so I said that that approximation is the gamma embedding into the metric ultra product, and stability can be shown to be equivalent to a lifting problem, where gamma lifts from the ultra product to the direct product, and second cohomology somehow gives you some lift. It doesn't give this lift, but one can turn this problem into some partial lifting problem, where in each step the kernel is an abelian group, and in fact a Hilbert space, and the vanishing of the cohomology then gives you the desired lifts. And these tools were later improved. So I'll just mention that in a paper by, so another theorem by Badel, Lubotzky, Sauer, and Weinberger. So G, that even though this is a curved brackets, these lattices in higher ranked groups with at least rank 3 are also typically Frobenius stable. So G, a real semi-simple Lie group with sorry. With factors of rank at least 3, then now I think it's in most cases. So in most cases, gamma is gamma is some lattice in G. Is once again Frobenius stable.
So the most is on the lattices or on the semi-simple?
I believe on the lattices. I believe. I think the groups always have continuous cohomology vanishing. Okay. And these vanishing in Hilbert spaces. So if we want to talk about stability in the p-Schatten norms, then vanishing in Hilbert spaces is not enough. We need vanishing in Banach spaces. And this was then improved by Lubotzky, Oppenheim, in 2020. That these same lattices, I will note the same gamma, are p stable, are GP stable for p strictly between 1 and infinity. Okay, so these Banach spaces somehow they are uniformly convex, and somehow these techniques of vanishing cohomology work for these two, and we can prove stability for these two. But yes, provided that L is large enough. Yes. Yeah. So there is also a work in progress of Bader, Sauer, and also Glasner, Goffine. No, Bader, Sauer.
So the same gamma is like lattices in real groups and lattices in periodic, but for large enough.
Yes.
Points.
And this left the open cases of p equals 1 and p equals infinity. And again, p equals infinity is the major open problem of groups that are not MF, and we resolved this in the less important case of p equals 1. But one might argue that the L1 norm is it's dual, but also from a theological point of view, emunah be'el echad. So one might argue that this is the most important norm. So
P is always a prime,
so theorem of myself, Dogon, and
By the way, you should ask Barry Mazer, whose father always asked him, and I think he was quite religious, why is 1 not a prime when you define prime numbers? Many non-mathematicians would argue that 1's a prime.
exactly. In fact, I did not. So I said these groups were stable, but I did not specify which groups are not approximable. So Deline in the 70s constructed for some gammas, say in symplectic groups, say symplectic, a lattice in a symplectic real group, constructed some central extension Z.
You need something in the middle, right?
Yeah, I need. Okay, so we can take the universal. I can call it tilde, but then it's not a finite central extension. Okay, okay, let's just call it
Put an F.
tilde. And it has some central extension which is not residually finite. And the basic observation is that if a group is both approximated by a metric and it is also stable with respect to that metric, then it is necessarily residually finite.
In linear groups or in
Yes, so if our groups are finite groups or linear groups, then a stable group that is approximated is always residually finite, and so if we find a stable group which is not residually finite, then it is necessarily not approximated by these metrics, and these extensions with that are not residually finite have the same cohomological vanishing properties, and so these are not approximated, again for large enough L, are not approximated by the p-Schatten norms. And so suppose we fix some gamma and some extension, and we can even assume that our kernel in the extension is Z over 2. We can find these groups with even a center of order 2 that is not separated, is mapped trivially by any map to finite groups. So it is not residually finite, and yet it is stable. Okay, so So for these gamma tilde, which we call Deligne extensions, gamma tilde is not G1 approximated. So how much time do we have?
11 and 10, that takes some.
Okay, so I'll just give a general idea of the proof, which again, I think these groups are in fact stable with respect to the with p equals 1 by your group, but we can show it without proving that, and the proof is rather straightforward.
So we don't know between all mass stability or down.
Currently not, but by an upcoming work they are. So
I'm a bit confused. Gamma is stable, but not gamma tilde. G1.
they are.
Now, what are you saying?
Neither of them are known to be G1 stable before.
Okay.
So these groups are, say, Frobenius stable, but not known if they are G1 stable. Okay, so we denote the central element J, and this J is in the RF kernel of gamma tilde, meaning it maps trivially for any homomorphism into a finite group. So since J squared equals 1, then, well, it is a basic exercise to show that a sequence of unitaries where un squared approaches 1 can be approximated by so it's an almost involution. It can be approximated by an actual involution. So we can assume that phi of j squared is actually 1, and well, up to conjugation it will be phi of j it has 1 eigenvalues and minus 1. So and if it has some separation, then this means we have at least 1 eigenvalue, which is minus 1. But then we have that the phi of j, its distance from the identity. So in the 2 norm, so we know it is separated in the 1 norm, but the fact that it has these only 2 eigenvalues means that this distance must be at least 2. Okay? So, and so if we assumed it was 1 approximated, then an asymptotic homomorphism in the 1 norm is in particular also an asymptotic homomorphism in the 2 norm. But the problem is that elements that are separated from the identity in the 1 norm are not necessarily separated by the 2 norm, but the fact that this kernel is finite, so we assumed it is of order 2, but it works for any finite kernel, means that the characters are somehow bounded from the identity, and this gives us that if it is separated in the 1 norm, then it must be separated in the 2 norm. So we have this separation. So if this kernel was infinite, we could have had characters arbitrarily close to 1, and we'd run into problems. Okay, so I think we'll finish here, and we'll wish a very happy birthday to Alex. And
Any questions for Benny?
Yeah, so for this square round bracket higher t, so for property t, like for automorphism or automorphism free group, there are other ways of proving things of t. Well, not nonlinear groups. Has anybody done that for like t sub n? Conditions that
you mean like
like this
Ozawa's criterion?
Yeah.
That's a good question, I think.
It's a very good question. So there is a checkable criterion,
Yeah,
and in fact Alon started trying to implement this, but I think it's really, really...
The matrices are too large.
yeah, I mean, so far, we just cannot.
but you got a condition, you've got a
We have a
criteria.
condition, yes. I mean, we have, for some time ago, with Piotr Novak, we have a condition, but recently Novak and Antonio Lopez Neumann came up with a suggestion for another condition, and with my son we proved that it is applicable for all the four, the condition. And this is, it's on the verge of doable. So
Okay.
far, the other
All right. It's a positive answer.
Can
Yes.
you do this with something different than two Z mods?
Yes. We just did it for ease of the proof, but yeah, I mean, when you have finitely many roots of unity, you can argue the same.
Right now, the largest P for which there exists a group that is not GP approximable is 2.
No, any p, any finite, any p, any p which is fixed.
This is
Yes,
Is this the first example of a non-G1 approximable group?
I think so. Yes. Yes.
So you prove this by showing that G1 approximable for groups of this type implies G2 approximable?
Essentially,
Yeah,
yes.
and is there a general, like GP approximable implies GQ approximable when Q is bigger than P?
So I think for when the kernel is finite, then yes.
Okay.
Otherwise,
Yeah,
Yeah.
for these groups.
Yeah, for these groups.
For some structure.
Yeah.
You can also show that if the group is MF, then it is hyperlinear.
Uh-huh.
yeah.
It's important to stress that usually for general group you cannot deduce from one norm